Hey everyone, today we're going to work on solving a quadratic equation by completing the square. First we need to talk about perfect square polynomials. So a perfect square polynomial, it's a polynomial that results from squaring a binomial. So let's just take a quick look at what that might be. Here, x squared plus 6x plus 9. Okay, so if I factor by grouping, 1 times 9 is 9. 6 there. What two numbers add to 6 and multiply to 9? They're both positive 3. So we'll split this x squared plus 3x plus 3x plus 9. And if I group those, take an x out of here, take a 3 out of here, I'm left with x times x plus 3 times x plus 3. And I'm left with x plus 3 and x plus 3, which equals x plus 3 squared. Okay, great. So there's also a little bit more of a shortcut we can use for that. X squared plus 6x plus 9 here. We just proved that it's x plus 3 times x plus 3. We can also use a little bit of a shortcut. If we see perfect square here, if we take the square root of that and we copy this symbol, square root of 9 is, let's use a different color here. I can't draw there. Square root of 9 is 3. And if we copy this symbol here, x plus 3 squared. So let's take that down to the bottom here. If I can move this. This bottom example, x squared minus 16x plus 64. If I see that, I can square root 64 and copy this symbol here. That's going to leave me with x, and then I've got square root of 64 is 8. If I do x minus 8 squared, that's going to be, so x times x would be x squared, minus 8x would be minus 16x, and then negative 8 times negative 8 is positive 64. They don't happen often, but when we do, we can take advantage of a perfect square polynomial, and we'll need to use that for completing the square. So completing the square is a method for solving quadratic equations that cannot be factored. We can use it when it can be factored. So I say it cannot be factored here. That's usually what we use it for, but it can be used in other times too. It involves turning one side into a perfect square polynomial and then taking the square root of both those sides in the equation. The procedure is quite long, so you're going to want to make sure you have this in your notes. So, number one, move the linear term to the left. We're used to seeing something like ax squared plus bx plus c equals 0. So we've got our quadratic term, that's ax squared, and we have our linear term, that's bx, well written, and c is our constant. So what we would need it to look like is ax squared plus bx equals negative c by moving that c to this side. Move the linear term to the left and constant to the right. Divide both sides by the leading coefficient. So we would, second step would be divide everything by a. If that's 1, we don't have to do anything. If it's another number, divide everything by a. Now, in a separate step, we're going to divide the linear term by 2. Our linear term is b, so we're going to divide that by 2, and we're going to square it. Why would we do that? So that's just going to be a separate part of it. If b is negative 8, negative 8 divided by 2 is negative 4, negative 4 squared, 16. That's just going to be another number that we're going to take. We're going to add that result to both sides. And then factor the left side, square root both sides, add, subtract, constant on the left. Steps 5 through 7 are going to be a lot easier during our examples to go through. So a lot of steps here, you're going to want to have them as we go through completing the square. Clear that. All right, let's look at our first example here. Actually, I'm going to pause. We got our checklist on the bottom. We have our equation on the top. So step 1, yellow. Move the linear term to the left and the constant to the right. All right, so we're going to subtract 4x and we're going to add 16. We're going to end up with 2x squared minus 4x equals positive 16. All right, divide both sides by the leading coefficient. Okay, leading coefficient is my a value. I'm going to divide everything by 2. 2 divided by 2 is 1 minus 2x equals 8. Great. Did step 2. Divide the linear term by 2 and square it. I'm going to use a different color here. Go over here. My linear term is negative 2. I want to divide it by 2 and then square it. Negative 2 divided by 2 is negative 1. Negative 1 squared is 1. So why do I need to do that? Well, that's going to give me a perfect square. I'm going to add the result to both sides. Go back to my blue color-ish. And I'm going to add 1 to both sides. Add 1 to both sides. What that's going to end up doing is giving me back to my standard form that I'm used to on the left and a perfect square on the right. Factor the left side. Okay, add the result to both sides. Check. Factor the left side. So I know from my shortcut earlier that I have created a perfect polynomial. So I'm going to take the square root of 1, which is 1, and I'm going to keep this symbol. So this is going to be x minus 1 squared, and that equals 9. X minus 1 times x minus 1 is going to be x squared minus 2x plus 1. And from here, I'm solving for x. Since I have parentheses there, I'm feeling good about that. I need to square root both sides. And I'm going to move some stuff here. So bringing it up here, I'm left with x minus 1 equals 3. Although it is not just 3, right? We have to account for negative 3 as well. So I have two solutions at this point. And sometimes this would be a sufficient answer. In this situation, it's not, because we can add 1 to both sides. I'm sorry, that's not a sufficient answer. X would equal plus or minus, it's not letting me write today, 3 plus 1. That might be a answer that we can use at another time. However, these are integers, so we might as well show our two solutions. They would look like this. Positive 3 plus 1 would be 4, negative 3 plus 1 would be negative 2. So we have solved for x by completing the square. Really complicated process. Here there might be other ways to do it, but it will really help in our second example here. 3n squared plus 24n plus 3. Looking at our first step, move the linear term to the left and the constant to the right. The thing I need to do is subtract 3 from the top here. I'm going to left with 3n squared plus 24n equals negative 3. Check on number 1. Number 2, divide both sides by the leading coefficient. All right, let's do that. My a value is 3. I'm left with n squared plus 8n equals negative 3 divided by 3 is negative 1. N squared plus 8n equals negative 1. What is my linear term? My linear term is 8. And what I'm going to do is divide that by 2 and square it. 8 divided by 2 is 4. 4 squared should be 16. I'm going to add 16 to both sides. And that's going to leave me with the following. N squared. Gave myself a little bit more room since the computer's not writing very well. Okay, so I've done steps 1, steps 2, steps 3, and steps 4. And I factor the left side. I have a perfect square here, which is how that's going to be set up. Square root that, leave me with 4. And a plus symbol there. N plus 4 squared equals 15. If I wanted to show that, n plus 4 times n plus 4, that would be n squared plus 4n plus 4n equals 6 plus 16. And that's going to get me back there. So I feel good about that. I'm going to take the square root of both sides. That leaves me with n plus 4 equals the square root of 15. If we put that into our calculator, we're going to get a decimal. We're going to leave it at root 15 for now, but we do need to remember the plus and minus symbol because negative output is also possible. All right, I factored the left side, square rooted both sides. Add or subtract the constant from the left, subtract 4, n equals negative 4 plus or minus the square root of 15. And that is a good final answer here. Don't need all those decimals, don't need all that. The square root could be reduced, radicalized, we've done that, but root 15 is fine. Negative 4 plus or minus the square root of 15. Remember, there are two answers here. One of them is negative 4 plus root 15, and one of them is negative 4 minus root 15. See you all in class.